The construction industry is currently facing major challenges. The energy crisis, rising construction costs, and shortage of resources call for new solutions. Reducing heating costs through efficient heat pumps plays a decisive role in this. The topic has never been as relevant as it is right now. My name is Vincent Gruel, and I am the team leader for commercial sales at PCT. Together with our specialist companies, we are looking for ways to build economically and sustainably. As the market leader for innovative screed systems, our products are part of the underfloor heating system. So we asked ourselves the following questions. Firstly, what influence does the screed have on heating performance? And secondly, what properties can we use to improve the heating performance? Let's take a look at the theory. The heat must travel from the heating pipe to the surface. Two properties play a role here. The lambda value defines the thermal conductivity and indicates how much energy or heat a material allows to pass through. The higher the thermal conductivity, the more heat reaches the screed surface. The second property is the coverage of the pipe. The further the distance between the heating pipe and the floor, the less heat reaches the top. High thermal conductivity and a thin screed therefore increase the energy efficiency of your underfloor heating. Things always look simple in theory, but we test both assumptions under real conditions. For this purpose, we set up an experiment to confirm the hypotheses. We created screed fields, each with 5 square meters of underfloor heating. Now we are looking at screed types. Retinol screeds with different screed thicknesses. To check how the temperature of the surface develops, we have installed thermal imaging cameras. With their help, we can not only visualize the differences on the surface, but also measure them precisely. And now I'll show you the first experiment. Firstly, we test the thermal conductivity of different screeds with the same screed thickness. Our first assumption: screeds with higher thermal conductivity allow more heat to reach the surface at the same boiler temperature. For this reason, we have installed the same nominal thicknesses with a heating pipe cover of 45 millimeters. The order of thermal conductivity starts with the calcium sulfate screed with the lowest thermal conductivity of 0.7 to 1.0 lambda. Then the cement screed, which we call the zero screed, with a lambda value of 1.0 to 1.5, followed by cord reducer 48, retinol reducer 48, and retinol extreme, with a lambda value of 1.6 to 2.4. For a brief explanation, the calcium sulfate and cement screeds are conventional screeds with no special properties. Cord reducer 48 increases the thermal conductivity of cement screeds and saves CO2, as the amount of cement can be reduced by 20%. Retinol reducer 48 also increases the thermal conductivity of cement screeds and saves CO2 by reducing the amount of cement by 20%. At the same time, retinol reducer 48 is ready for covering after 7 days with a shortened heating phase of only 6 days. Our premium product Retinol Extreme has the highest thermal conductivity and is ready for covering after 5 days with a shortened commission cycle of only 4 days. The first thing we check is when the fields have reached an average temperature of 25 degrees. The flow temperature, meaning the water temperature with which the fields are heated, is 40 degrees. Let's take a look at the fields through the thermal imaging camera. First, Retinol Extreme, cord reducer 48, retinol reducer 48, then the zero screed, and finally the calcium sulfate screed reaches 25 degrees. This means that a retinol extreme screed reaches your comfort temperature 65% of the time compared to the calcium sulfate screed. Now we look at the fields after there has been no further change in the surface temperature, and the fields have therefore reached their maximum temperature. The most important thing is, of course, the average temperature on the surface. Let's start with the calcium sulfate screed at 27.1 degrees, zero screed at 27.7, retinol reducer 48 at 28.5, cord reducer 48 at 28.8, and retinol extreme at 29.1 degrees. The retinol extreme screed is therefore 2 degrees warmer than the calcium sulfate screed. The conclusion is that the higher the thermal conductivity, the higher the temperature on the surface, and the faster the underfloor heating reaches your desired temperature. In the second experiment, we would like to test the second assumption that a thin layer screed in which the heat has to travel a shorter distance to the surface is better than a thick screed. In the two rear panels, we have a calcium sulfate and cement screed with 65 millimeter pipe coverage. And in the two front panels, we have retinol X thin, retinol extreme with 20 millimeter and 30 millimeter pipe coverage. Let's switch on the thermal imaging camera and take a look at the results. Retinol X thin reaches the 25-degree surface temperature in only 45% of the time. The difference in surface temperature between calcium sulfate and retinol extreme is 3.3 degrees. The assumption that a thin screed increases the heating performance of your underfloor heating is therefore also confirmed. As mentioned at the beginning, retinol extreme, cord reducer 48, and retinol reducer 48 increase the thermal conductivity. At the same time, the screed thickness can be reduced compared to the standard thickness in residential construction of 45 millimeter pipe cover. What does this mean? We compare the pictures and see that with cord reducer 48 with a pipe cover of 35 millimeters, 0.6 degrees more is achieved on the surface than in the field with 45 millimeter pipe cover. We can see that reducing the pipe cover by 10 millimeters increases the surface temperature by 0.6 degrees. We now carry out the same test again with retinol extreme with 30 millimeter pipe cover instead of 45 millimeter. Reducing the pipe cover by 15 millimeters actually increases the surface temperature by 0.8 degrees. The all-important question: how much energy can we save with retinol screed? The heating curve for heating systems illustrates the possibilities we will have in the future. The function describes how much flow temperature the underfloor heating runs at, depending on the outside temperature. The colder it is outside, the more flow temperature is required to reach the comfortable temperature in the house. Logical. A retinol screed reaches the desired temperature on the surface in around 60% of the time, compared to a conventional screed. A flatter heating curve can therefore be used. As more energy reaches the room at the same flow temperature, a retinol screed can generally be heated with a lower flow temperature. This means that the curve is not only flatter, but can also be shifted downwards in parallel. As a result, a retinol screed reduces your overall heating cost by around 5 to 20%. Why does a retinol screed have improved thermal conductivity? This is due to the higher strength, bulk density, and reduction of air voids. We recommend the following retinol screeds. The basic variant is cord reducer 48 with 35 millimeter pipe cover if you have no requirements for readiness for covering. The standard variant is retinol reducer 48 with 35 millimeter pipe cover, ready for covering from the 7th day, and a shortened heating phase of 6 days. The highest performing screed is retinol extreme, which can be installed with 30 millimeter pipe cover, is ready for covering after 5 days, and has a shortened heating phase of just 4 days. When we planned the trial, we didn't realize that the screed would play such a major role in reducing heating costs. We are proud of the performance of our products. Retinol screed is an absolute game changer and offers a solution towards climate neutrality for your building projects.